Okay, welcome all of you in this afternoon session. Good afternoon, Jim. Do you hear me?
Yes. Can you see my screen?
But we don't see you at the moment, but that will come anyhow. It's a good test.
Oh, is this Dirk?
Yes,
Hey, Dirk, how are you?
I am good, yes, and then nice to see you now on the screen. I had hoped to meet you here, but perhaps some other time.
Hopefully.
So this is the talk which should take place 2 or 3 hours ago, but due to technical problems, it's now here, and the exercise section will be at some moment afterwards. We have heard already a lot about determinantal singularities, but we looking forward to your talk.
Thank you. So should I begin? I guess so. Okay. First of all, I am grateful for people who, after tried to suffer through my beginning earlier this morning with this, come back to try again and see whether I can do a better job. It seems to be working now. And I was going to say, I'm sorry that I can't be there with you. And given the trouble I had with the computer, it would have made even nicer to be able to be there and enjoy the conference with all of you. Already, Terry and Maria, and in fact, the first lecture of Matthias, had begun talking about certain aspects of determinantal singularities. I'm going to enlarge that and talk more broadly about what we'll call matrix singularities, but it will include M by P singularities, at least certain aspects of it. In particular, I'm going to be talking about the topology of these singularities and introduce two methods which turn out to be pretty useful in trying to understand the topology of these singularities. The starting point, of course, is the standard reference point for the topology of a Milnor fibration if we have F from Cn plus 1 to C defining a hypersurface singularity. It has a Milnor fibration which lies over a sufficiently small punctured ball, B delta star, and inside of a small ball, B epsilon. And the fibers, the inverse image of any point, is the Milnor fiber, and it's well known, has been described earlier. You can use Morse theory to determine the topology. It's n-1 connected. It's a bouquet of n spheres. And there's an algebraic formula for the number of spheres, the Milnor number, which is the dimension of the Milnor algebra, which also, from a deformation theoretic point of view, happens to be the RE codimension of F. And then lastly, there's the link obtained by intersecting x0 with the boundary sphere of this ball. And this also has nice properties. And then there are various methods for getting information about the whole Milnor fibration by using monodromy and relating this to properties of the link. When we go on to non-isolated singularities, even hypersurfaces, complications set in. And in fact, if we take a hypersurface singularity V0, where the dimension of the singular set is K, then by a theorem of Kato-Matsumoto, the Milnor fiber can lose connectivity by this degree. So it may only be n-1 minus K connected. So in terms of cohomology, it will continue to be 0 up through dimension n minus K minus 1. But now there's a question mark of what happens from n minus K up to n. So in particular, the larger K is, the larger this region of uncertainty enters into it and trying to understand it. Also, the link is no longer a manifold, but rather is a real analytic set whose singular set will be as real dimension 2K minus 1. So the question is, what happens in this case? In particular, can it still be a bouquet of spheres, and of which dimensions? And in fact, the introducer of my talk, Dirk Siersma, was a person who sort of pioneered, along with his colleagues, work on looking at properties of these non-isolated singularities, at least for small dimension of singular set. And he used two things: the property of the singular set, for example, could be an ISIS, and special transverse types of the mapping to the singular set. And in a number of cases, they do obtain as a bouquet of spheres, but now the spheres can have varying dimensions from n, n-1, even n-2. Okay, matrix singularities complicate things because they can have singularities of much higher dimensions. And so we need a way of trying to deal with this large range of uncertain dimensions here. So, and let me put this in perspective then. So we have the class of all non-isolated singularities, and down here we have matrix singularities. And what we're going to do is think of matrix singularities as sitting in two subclasses of non-isolated singularities. One of them, which we're going to call the singularities of universal type B, is a way of taking a given fixed non-isolated singularity and working with nonlinear sections of it. The second is to bring Lie group methods into this by looking at varieties V, which arrive as what are called exceptional orbit varieties of prehomogeneous spaces. So all these terms I'm going to define, but this is just to give you a perspective. And the goal is going to be to talk about the methods that work for each of these larger classes and how what results do they give in the case of matrix singularities. So what do I mean by the category of singularities of type V? So we take V sitting inside of Cn, say, and we take a germ, F0, from C little n to C capital N, and we just pull back V by F0. And that we'll think of as V0. Although I'm going to refer to this as nonlinear sections, we actually allow little n to be arbitrary. It could be much bigger than capital N. That's okay. The second thing is, notice I'm using the term category of singularities. Normally, we just think of a singularity in and of itself, but in fact, it turns out it's very convenient to think of this as a category of these singularities for a fixed V. So what are the morphisms for this? So if we take a morphism from, say, W0 to V0, W is going to be of this type. It's given by G0 inverse of V, and it's defined by some G0 mapping into Cn from P. And such a morphism is induced by a germ from Cp to Cn so that G0 is obtained by F0 composed with phi tilde. So we have both objects and morphisms, and this will be important later when we talk about characteristic cohomology, where we want to know that it has good properties with respect to this category. There's also a subcategory of those defined by F0, which are transverse to V in appropriate sense. This is going to often be the case. And then the codimension of the singular set of V0 will be the same as the codimension of the singular set of V. So because things like matrix singularities can quickly have high dimensional singularities, this will also occur for V0. Okay, so what are some examples of universal singularities V and singularities of type B? Well, if we take a discriminant of a stable germ, and we can take the discriminants of finitely determined germs with the same local algebra, those discriminants arise as a nonlinear section of this discriminant of the stable germ. Similarly, if we take a bifurcation set of a versal unfolding with respect to some equivalence G, and we take a non-versal G bifurcation set of an unfolding, it is obtained as a pullback here. And here G can not only just be the standard groups you're familiar with, like A, K, and R, there's a larger collection of groups to which this equally well applies. Thirdly are central hyperplane arrangements. I think today I heard Matthias, before I was dealing with the IT people, refer to Coxeter arrangements. These are a collection of hyperplanes through the origin. We can think of that as a germ of a variety. And you can pull that back. If it's a linear section, you'll get a hyperplane arrangement, but it can be nonlinear and you get hypersurface arrangements. Fourthly, an important class of things which I will shortly describe are exceptional orbit hypersurfaces of prehomogeneous spaces. And these include not only the kinds of things we'll be interested in matrices, but include things like they enter into things like working with quivers and also with certain kinds of factorization problems where you have varieties which obstruct the factorizations. And then lastly, at the bottom, we actually have the variety of singular M by M complex matrices, which may be general, symmetric, or skew symmetric. And in that case, these three cases, you actually get hypersurfaces, and or more generally, as Terry and Maria and Matthias talked about, general M by P matrices and the pullbacks of these. So these are the kinds of things which anything where we talk about with singularities of given type, potentially we could be including some of these as well as matrix singularities. So what are some examples? Well, I can quickly go through these because Maria has already talked about, like if you take a linear mapping into the 2x3 matrices, and you look at V being the matrices of rank less than or equal to 1, you can pull that back, and provided you have the right transversality conditions, you get a Cohen-Macaulay singularity by the Hilbert-Birch theorem, and it's given by the three 2x2 minors. If instead we go up to isolated surface singularity in C5 given by mapping into the 2x4 matrices, again, we have the variety of singular matrices of map less than or equal to 1, but now, and V0 is defined by the idea of the 2x2 minors, but now it's more complicated because one of the things, this is the so-called Pinkham example, that there are ways of deforming this abstract singular surface, which is not given by just deforming the entries of the matrix. My own personal interest in this actually arose quite a while ago, and here's an example of a mapping into, notice in this case, these are 5x5 matrices, but they're skew symmetric. So this adds an extra interesting feature to these kinds of singularities. Among others, all 5x5 skew symmetric matrices are singular. So in fact, the variety V, we want it to be those matrices which have a greater or a lower rank, and that means in this case rank less than or equal to 2. And V0 is not defined by determinants in the reduced form, it's defined by 4x4 Pfaffians of this matrix. So you get these 5 equations here. My interest originally arose in this because this happens to be an example of a unimodal singularity. In particular, if you were to put in these two zeros here, say lambda times z, lambda is a parameter which changes the analytic type as you deform it. And so there's a question of being able to understand a type of equisingularity for these families. And in fact, that there's a strong form of equisingularity where even when you include the full unfolding of this, which means adding another 5 variables to these other entries, the whole versal unfolding is topologically a product along this. To do this required using a form of classification of sections of these varieties. And lastly, all the preceding examples were all linear maps. In fact, that was not intentional. In fact, equally well, you can consider nonlinear maps. In fact, Bill Bruce classified simple symmetric matrices. And in mapping from C2 into the 2x2 symmetric matrices here, you can see that the singular variety is given by the determinant, which is x squared y minus y to the 2k, and which is a singularity of type D, 2k plus 1, which is one of the simple hypersurface singularities. And in fact, he discovered that basically every simple hypersurface singularity can arise this way, except for E8. There's been further classification of different types of symmetric, skew symmetric matrices and so on, just to give you an idea that there's a relatively rich body of material in this. So what is my goal or our goal in trying to understand this? We want to understand the topology in the hypersurface case, where V is a hypersurface, understand the topology of the molar fiber of V0, because it'll be a hypersurface singularity. And in general, even allowing non-hypersurface Vs to understand the topology of the complement and the link of it. So in particular, when you come up with these matrices, there are going to be cases where they're not hypersurface singularities, and then there's still the question of the topology of complements and links and so on. To understand this, we understand it not just as a single object, namely the cohomology of one of these fibers, but really break it up into two parts. So there are two contributions to this. One part is the contribution that comes from the topology of the germ F0 and the way it interacts with V. And in fact, in this situation, we might expect that somehow there might be some kind of analog of what happens in Milner's situation, or more generally isolated complete intersection singularities, and that maybe some kind of Morse theory type arguments might come into play. But there's a second thing which can enter into it, and that is the contribution inherent from the topology of V. So this requires us to do two things. One, to figure out what the topology of V will be with the Milner fiber complement and link, and to figure out how this topology is inherited by V0, what part of it continues to persist at V0. And there's actually a third part to this, namely, when to determine how these two contributions combine to give the topology of V0. So that's what we're going to do. So let me now overview of the main points of this. So we're going to do two things. So we have two things in mind. We have this idea of the category of singularities of a given type, and ultimately we're going to bring in Lie group methods to work with this. So basically, for the singularities of type, what we're going to do is use a stabilization of the non-zero nonlinear sections to obtain something that's kind of like a Milner fiber, but it's a singular Milner fiber. And in fact, this kind of goes back to work David Mann did when he was looking from C2 to C3, and he was stabilizing the germs, and the corresponding discriminants that he got from stabilization turned out to be a type of nonlinear section of a stable discriminant. So this is going to involve, in some sense, equivalence groups for these nonlinear sections. We want to talk about how we can determine the topology of these, quote, singular Milner fibers. Hopefully, it's going to bring into it some deformation theoretic information arising from these equivalence groups. So it's something the analog of the Torina number. And then this is, which is a codimension of certain tangent spaces. And then to ask under what circumstances we can obtain analogs of what's typically called a mu equals tau result, where mu is going to represent some invariant of the topology, maybe something like a Milner number, and tau is going to be some kind of invariant, like one of these, like the Torina number. That's for the first question, A. And for the second question, B, is going to be introducing characteristic cohomology for the singularities of type V. So as I said, this is should capture the topology of V0 inherited from V. It should be for not just the Milner fibers in the hypersurface case, but for complements and links all at the same time. And we're going to do this in such a way that it has certain invariance properties with respect to these groups of equivalents, and also functorial properties, because we know this is a category. So hopefully, if we're going to talk about cohomology in the category, it's going to have nice functorial properties. And then lastly, we need to, so if you produce classes which are inherited from B, there's a possibility they could still be vanishing. So we need to detect the non-vanishing of these groups. The way we get at this is where especially Lie group methods come in. And this is where the Lie group methods for something called the exceptional orbit varieties come into play. And then we can apply these to Lie groups. Okay, so let's go then and begin to fill in some of the details about these equivalence groups and their properties and how exactly they connect up with the topology for question A, problem A. So there's an old thing that kind of goes back to when I was looking at these skew symmetric matrices. There's an equivalence, a way of extending K equivalence, which we learned about earlier in some of the talks, to a type of K equivalence which preserves V. So what we have here, K equivalence in this diagram would normally be given by a phi, which acts fiber-wise on N, Cn, and lies over this local diffeomorphism on C little n. And in there, for K equivalence, you only have to preserve in each fiber the origin. Well, what KV equivalence does, it preserves not just the origin, but V in each of these fibers. So this gives a group which turns out to have properties in some respects comparable to the kind of properties we have for K. We can refine this. Namely, we have phi not only preserving V in each fiber, but we can actually preserve the a defining equation for V. That is, it's not going to just preserve V, but it's going to preserve all the fibers of H in each fiber. So this is something where if we have like a Milnor fibration for V, this is going to capture some properties of the Milnor fibration under the equivalence. And then thirdly, there is the group which has been standardly thought of for matrix singularities. It actually arises from having a representation G of a group on, let me see if I can get this out of the way, people can see. I don't know whether you see the same thing I see. Representation of G on Cn. And what you want for this phi is for an action of elements of B, which vary with each point, acting on F0 in this case. And then we compose with little phi again as below. This works for any group G, and this is a type of gauge type equivalence. In the special case for matrix singularities, there are specific G's that act on different space and matrices, and I'll reserve K sum M to reserve for that special case when we get to it. Okay, let me see. Okay, so with these equivalence groups, you know, when you have R or A or K, you have their tangent spaces, the deformation tangent spaces, which are sometimes referred to as the extended tangent spaces of these groups. We can do the same thing for these equivalence groups here. The crucial thing that comes in for this V is the modular germs of vector fields tangent to V, which consists of those vector fields or germs of vector fields, theta n, which send the ideal of germs vanishing on V to that ideal. These have the property that they're going to be tangent to V in the sense they'll be tangent to appropriate strata of V. There's alternate notation for this. So I'm not going to go into it, but if you see something like Dirac log minus V in the hypersurface case, this was originally introduced by Saito, and in fact, if you go beyond the case where V is not a hypersurface, it's not so clear what exactly that should mean. So I'm going to stick with Dirac log V. So you've already seen that the group Dn germs of diffeomorphism that has extended tangent space theta n. So if we write down the generators for Dirac log V as a module over On, we can write down the tangent space for what this is called, extended tangent space. It's just df0 applied to theta n plus the On module obtained by pulling back these vector fields by composition with f0. So we can actually write it as a module like this. And when you write it this way, it starts looking not so different from the kinds of things you would see maybe for like K equivalents. If V is a hypersurface with the defining equation H, we have this other group KH, and we can obtain the corresponding tangent space for it by replacing dV by Dirac log H, which are the vector fields which annihilate H. And this means they will stay in the tangent to the fibers of H. Okay, so having done that, let's connect this up a little bit with geometry. Again, we're basically going to be following ideas due to Kyoji Saito. So we can define what's called the logarithmic tangent space of this variety V at a point y by taking all the vector fields in Dirac log V and evaluating at y. This is going to be a vector space, and in fact, it's a subspace of the tangent space to the stratum of the canonical Whitney stratification of V containing Y. The reason this is true is because the canonical Whitney stratification is invariant under diffeomorphisms. So if you take a one parameter curve from one of these vector fields and integrate it, it's going to stay in the same Whitney stratum, and therefore the tangent vector will be tangent. We can look furthermore at a submodule of this, namely the Dirac log H, and look at those vector fields. Again, it's going to be a tangent space, and we have this inclusion of tangent spaces. T log H contained in T log V contained in the tangent space to the canonical Whitney stratification. And there can be a relation between these. Namely, after CITA, we say that V is holonomic if the second inclusion here is the identity for all of y in the neighborhood of 0. And moreover, if both inclusions hold, we actually going to refer to this as being H holonomic. So let me just remark all those examples that I described earlier. I talked about discriminants of stable germs, bifurcation sets, hyperplane central hyperplane arrangements, and also the varieties of singular matrices. All of them turn out to be holonomic. In the case, for example, discriminants, that you are in the nice dimensions, so that basically you don't have moduli appearing, because the moduli would destroy this property. And in fact, it's true that they're even kind of H holonomic. So these two properties are fairly common properties, and they have as a consequence a way of relating algebraic properties of F with geometric properties. So we say that F is algebraically transverse to V if transversality holds with this logarithmic tangent space in place of the stratification tangent space for all y in V. And if V is holonomic, algebraic transversality V is equivalent to transversality to V, meaning to the canonical Whitney stratification. So you have geometric transversality being guaranteed by this algebraic condition. So with that said, it turns out then that just as for isolated hypersurface singularities or isolated complete intersections, that you have basically the complete Tom Mather approach for matrix singularities. All three groups, for all of these, the basic theorems of singularity theory hold true. And in fact, I wrote up here relevance for matrix singularities. In fact, it's in general for these sections of singularities V. And furthermore, the finite KV determinacy of F0 is equivalent to this algebraic transversality of F0 to V. I think Terry Gaffney made some reference to certain aspects of this in connection with M by P matrices, but it holds in general. In fact, it even holds for all of those special type of universal singularities that define. And furthermore, as far as classification methods, the really refined classification methods due to Bill Bruce, Andy Duplessis, Terry Wall, Kirk, etc., can be brought to bear in doing the classification for these things. So what's the connection between these different groups? Well, if both F in the hypersurface case are both weighted homogeneous for the same sets of weights, then the extended tangent spaces for both of these are the same. So whenever we're working with weighted homogeneous germs, it turns out that we can move back and forth between this, which is going to capture, as long as we have holonomic case, the transversality, and it's going to equally well give us the finite H codimension as well. So then we come to the situation with matrix singularities, because what I've described so far applies pretty generally. So for matrix singularities, it turns out by results of a number of people that the matrix equivalents for the groups of matrices turns out to have the same tangent spaces as for KV. So why is this? So now we come finally to the role of groups coming in. The preceding applied without any really groups being mentioned per se, as far as the groups acting on the spaces, the finite dimensional groups. It was always the equivalence groups. So here, suppose we take a representation of a finite finite dimensional Lie group. In fact, we're going to stick to the case where it's a complex linear algebraic group. So for those people in the audience that really don't have a good feel for this, you might think of G as being like GLNC, the invertible n by n complex matrices. And that will give you a good idea of some of the kinds of things we're going to do here. In the second lecture, I'll be more specific about other kinds of groups which can come into play. So if we take such a group and suppose its representation as a property has an open orbit. In this case, because of the algebraic nature of this, so first of all, this is what is referred to as a pre-homogeneous vector space, and it's due to Sato. But one of the properties of this as a consequence of the algebraic properties here is that the complement is a variety, and I'm going to refer to this as the exceptional orbit variety. It's a variety of orbits of positive codimension. So there's been a fair bit of work done with these pre-homogeneous spaces. Sato and Kimura actually classified the ones which can arise from irreducible representations of this important class of semi-simple algebraic groups. So that's done. But from our point of view, for matrix singularities, we can look at the actions of GLMC on the spaces of first M by M matrices, which I'll denote by M here. We can do it in all three cases. If we're looking at the general case, we only have to look under general left multiplication. But if we're looking at symmetric or skew symmetric cases, in the skew symmetric case, I'm going to restrict to the case M even here, we multiply, we act by a symmetric skew symmetric matrix A by the action of an invertible matrix B is by multiplying by B on one side and B transpose on the other. And this preserves the property. The exceptional orbit varieties for these are hypersurfaces in these three cases. And in the first two cases, for the general or symmetric, so M denoting the M by M symmetric matrices or the M by M general matrices, this for hypersurface is defined by the determinant. But in the case of skew symmetric matrices, when M is 2K, instead, to get a reduced equation for the variety of singular matrices, you have to use the Pfaffian. So the term determinantal is fine, except when you start getting to these questions, and you start getting non-reduced structure when you use determinants, and you really have to go to the Pfaffians. At the bottom of this, you can sort of see for M by P matrices, you just have the product of GLM cross GLP acting on the space of matrices. And these were the kind of situations that Terry and Maria, and to a certain extent, Matthias were talking about. Okay, so how am I doing here time-wise? Okay, just trying to see. Okay, so what we obtain as a result of having such a representation of a complex Lie group, we have its Lie algebra. And what we have down here, so if we have a representation of G, it's a Lie group homomorphism in the GLCN. And on top of it, we have the corresponding Lie algebra homomorphism from the Lie algebra of capital G into the Lie algebra of GLNC, which is just the N by N, capital N by capital N matrices. As each element of GLNC is actually a diffeomorphism of Cn, it gives you a local diffeomorphism. So we also have a map I going there, and there's a corresponding Lie algebra here. In fact, I've written theta n. I really should have written the vector fields in theta n that vanish at 0 here, so multiplied by the maximal ideal. But then we have a corresponding Lie algebra homomorphism here. So when we have this configuration, what can we do? Well, we can send any element of G all the way across. These are Lie algebra homomorphisms all the way over to here, and we get a vector field over here, which I'll denote psi sub u. So let me just give you an example for GLM acting on the skew symmetric matrices by BA goes to BAB transpose. The corresponding vector field for an element C in the general Lie algebra general linear group, which is just an M by M matrix, acts on a skew symmetric matrix A by just CA plus AC transpose. This is gotten by differentiating this equation, basically. And this remains, so this actually defines, it doesn't look like it, this defines a vector field on the space of skew symmetric matrices. The important thing about this is in the case of pre-homogeneous spaces, if G has an open orbit, then the exceptional variety E, then all of these vector fields are tangent to E. So they give us entries in der log E. And in fact, what the results of those, the people I'd shown before, say that their log E is actually generated by this module of vector fields generated by these in this case. So you can go through and take C to be the successive basis for these elements, look at those, and then you get a module generated by that, and that gives you all the vector fields that you're going to have. Okay, now, so we want to get to matrices finally to finish up here, but I do want to mention that it turns out that matrices, the variety of singular matrices, is not, in some sense, have the nicest properties. There's a condition which was introduced by Saito, which actually captures much nicer properties for especially for hypersurface germs, and that is they're a free divisor if their log V is a free OP module, which necessarily has rank P. And Saito, he gave several criterion for this, but basically, if you have P vector fields and you write them out in local coordinates, then, and these are in der log V, then if you look at the coefficient determinant, if this defines V with a reduced structure, then V is a free divisor, and this is generated by these. And this turns out to be extremely useful in getting at the working with the tangent spaces to the equivalence groups. So let me go back here. So, for example, of those many examples I described before, here are some examples of ones that are determined to be free divisors: stable discriminants, R-versal bifurcation sets, Coxeter hyperplane arrangements, and in fact, there's a whole class of more general cases where, in fact, you get, provided they satisfy two conditions here, you actually get that the bifurcation sets are free divisors. So free divisors are plentiful, and the question is, how do we get to use them in the case of things like matrix singularities? So if we take one of these representations of G on V, there are special cases where the dimension of G equals dimension of V. In this case, the exceptional orbit variety is a hypersurface. So two examples are Booklights and Mon. They basically showed that when you have reductive groups operating on what is called the representation space for quivers of finite type, that in fact these always give free divisors. And in fact, an example is if you take GL2 cross, so C star means C with zero removed by multiplication, and there's a factor you can divide out by, acting on 2x3 matrices, then you get a free divisor in there. And what is it given by? It's given by the product of the 2x3, 2x2 minors of that. And I'll point out this contrasts with the definition or the variety that you actually get for the space of matrices, where it's the common intersection of the 2x2 minors. So somehow there starts being relation between free divisors coming in and certain interesting singular varieties that we're interested in understanding. A similar thing happens, for example, in the case of symmetric matrices, except now here we use what are called solvable linear algebraic groups, and there are certain conditions where, again, we can deduce that the exceptional orbit varieties are free divisors. And one that's especially relevant, if you look at the action of the lower triangular matrices, BM, group of lower triangular matrices, acting on the M by M symmetric matrices, then E is a product of, sorry, I left something out. The product of the determinants of these upper diagonal K by K submatrices. So for example, what the defining equation for this will be, you take the upper 1 by 1, then you take the upper 2 by 2, and so on down the line. You take the product of those determinants, that happens to be a free divisor. And it turns out it's going to have better properties than just a single determinant of these. So let me now try to bring everything together. So suppose we have, and let me do it for the hypersurface case, because I think Terry and Maria and Thais have talked a lot more about the M by P case. Suppose we have a hypersurface singularity, and it's holonomic, which I point out it occurs in many situations. And suppose F0 has finite codimension. Then what you can do, you can stabilize this, you can deform it so that for t between 0 and delta, this is transverse to V. And this is because you can do it geometrically transverse, and therefore it's going to actually be algebraically transverse. In this case, if we have a hypersurface, the inverse image of V itself is going to be a hypersurface, and the inverse image of V under this perturbation is going to be the analog of a Milnor fiber. It's like a singular Milnor fiber for the stabilization. And one of the first things that David Mann and I did back when we were looking at questions about discriminants was to see that the result of Ley, even though it seems to be applied in a totally different situation, the mapping on a complete intersection, can be seen to apply to this situation so that Vt is homotopy to equivalent to a bouquet of spheres of real dimension n-1, whose number we denote by this. So let me emphasize, this says that for any of the n by n matrix singularities, they're all hypersurfaces that I talk about. If you do this procedure, you're going to get something that's the analog of a Milnor fiber. It's homotopy equivalent to a bouquet of spheres. The tricky part comes in is how many spheres do you get? And the nicest answer turns out to be for the case where V is one of these H holonomic free divisors. And then we can use the algebraic properties of the tangent space and use a result of Dirk-Siersma, which is a form of complex Morse theory, in order to give a formula for the singular Milnor number, the number of these spheres, in terms of these KH codimension. And I'll say that this KH codimension, which is the quotient here, this module has very nice structure, and it's kind of like a nice module version of a complete intersection algebra. So it's very easy to work with algebraically. The other thing I'll say is that if n stayed below the dimension of the singular set of this, when you do this perturbation, you miss the singular set, so this remains smooth, and you actually just get a Milnor fiber of H composed with F0. So let me show you an example of this. So here we are with, okay, I've just got a few minutes left, so let me try to go quickly through this. But just to illustrate this, if we take this germ that I have here, F going to X, comma X, Y, Y to 6, this is germ whose A codimension is 6. Its discriminant is defined as a nonlinear section of the discriminant of its stable unfolding. This simple looking discriminant. It's not very interesting. It's real picture. All right. But if we deform it, if we deform the mapping, we're going to deform its discriminant so that the discriminant becomes a stabilization of the section of this the stable unfolding. And what we get is this picture right here. You can see in this picture, there are like 6 cycles going around here. And this is actually homotopy equivalent to a bouquet of 6 spheres. So what we have in this case is 6, which is the AE codimension. And over here, this number, because this is in the framework that this applies to, is also 6. And I don't know whether you can see it because there's something hiding on my screen. But the AE codimension, this KH codimension, is the same as the KV codimension. And in fact, there's a general result that in the nice dimensions, these two middle numbers are always equal. So in fact, this is how we recovered the result, that when you deform the discriminant in the nice dimensions of a weighted homogeneous germ, in fact, then you get a bouquet of spheres, and the number of spheres is exactly the AE codimension. So this is an analog of Milnor's result. So lastly, just quickly finishing, what happens with matrices? It turns out that here, the simple example discovered by Bill Bruce began to motivate a lot of problems in understanding whether there's analogous results for sections or matrix singularities, which are nonlinear sections of these families of matrices. And in fact, what he discovered is that, remember that earlier example where he got 2k plus 1, we know what the Milnor number is, and he did the calculation here, and he discovered it's the same. Now, on the one hand, because this is below the dimension of the singular set, it's the same as just the singular Milnor number. And the other hand is because these two numbers are the same, this gives the kind of result that David Mond and I got, except now, in general, this is not a free divisor. So what happens is that corrections are needed for working with these matrices, taking into account the fact that it's not a free divisor. And in fact, there are two methods that are available due to Victor Goryunov, David Mond going one way, where they considered small n but arbitrary size matrices. And Brian Pike and I went the other way. We looked at arbitrary size n, but just small size matrices. And what happens is that in general, and here are the limitations on n in this case, because it's staying below this, there's a correction factor here, which has to be introduced for the Cage codimension, which is given in Victor and David's case by a homological invariant from a Tor sequence. And in the case that n is below this codimension, they show this vanishes, and that's why in the symmetric case, we have Bill Bruce's result coming true. But if you involve arbitrarily large size n, you can have very large size dimensional singular sets when you do this. And because of this, it turns out there are a number of terms that enter into the computation of singular Milnor number, but they're terms that geometrically have meaning by certain free divisors of the types I talked about that occur from certain other group actions. And these are all computed by one of these codimensions. And this continues to hold for 2x3 matrices. But as an example of this, if we go to what Bill considered 2x2 symmetric matrices, it turns out the interesting free divisor that comes into play is not given by the determinant, which is not free, but by multiplying it by A11 in this determinant. This turns out to be a free divisor. So we can compute its singular Milnor number by this KH codimension, and the other terms that enter into this sum turn out to be things that can be viewed as Milnor numbers for isolated hypersurface or a complete intersection singularity, and can be computed by the Legros formula. So I'll just finish by saying this throws out a huge challenge. This method allows for arbitrary size n and arbitrary size singular sets, but for small matrices. David Mond and Victor Goryunov could take any size matrices, but they can only do it for certain small n. So a wide open problem is to somehow, maybe either using one method or the other, somehow figure out a way to be able to do this for all n and all size matrices, and be able to bring together a complete understanding of this process for the first question A for the case of matrix singularities. So on part B of the talk tomorrow, I'm going to deal with part B and introduce characteristic cohomology to deal with the other question and see how these two approaches come together at the end. Thank you. I hope somebody's still listening there. Hello?
Thank you very much, Bill, for your amazing lecture. Even amazing is that it took exactly 45 minutes.
Did I finish at 45? Okay.
Yes, you're good at that. Other questions?
Could I have one comment, Dirk?
Yes, but Maria will ask something.
I know I've went through this quickly, but I have given to the organizers the Beamer handout file for this. So for people who are interested, you since I've gone through it quickly, you can go back, look at that, and see more slowly all the details of these things. And any questions they have later, just contact me. I'll be glad to try to answer them for them. Sorry. Anyway, go ahead.
Okay, sitting here.
Thank you, Jim, for the so nice talk. You remarked that in the case of general m by n matrices, the vector fields of the tangent space of the action of GLM cross GLM in the generic determinant of variety, right? Gives generators for the der log of the variety, right?
That's true. There are these papers by those names I gave, which actually did this. There are three separate papers, and they did it one for the symmetric, one for the skew symmetric, and one for the, I think, M by M. I assume there's probably a comparable version for M by P, but I don't know for certain. But I suspect that must be true.
Yeah, but I wonder if when you have an EIDS, right?
Yeah.
That the tangent space will, the generators of the tangent space of that group will be given by the pullback by F of the vector fields tangent to the generic determinant of variety. Can we still say that they generated their log? Maybe not, right?
Well, I don't know about the der log and the pullback, but as far as the universal singularity, what I'm calling universal singularity, I think it generates that. So that's what comes in for that extended tangent space. So when you compute the extended tangent space, what I called Km, you would get the same tangent space as if you can effectively say, look, you've also computed the extended tangent space for KV in that case. That's what I think is true.
Okay. Thank you.
And then when you pull it back, I agree with you. When you pull it back, I think up to finite codimension, you have the vector fields that are tangent to the pullback variety, but I don't think in general they agrees exactly.
Yeah. Yes. Thank you.
Sure.
A comment on that. I think in the case of matrices, you can use the group action to show that all these logarithmic tangent spaces and the tangent spaces of the Whitney strata they agree. I haven't checked the skew symmetric case or the symmetric matrices in particular, but I don't expect anything to go wrong there.
That might be true. That might be true. The special nature of the matrix singularities might make that true. I think there are other types of universal varieties where it actually fails, but it may well be, could be absolutely right, that it works okay for the case of matrix singularities. Thank you, Mr.
I think a discussion of this is also in the survey by Anne and me on the archive.
Oh, it is. Okay.
I saw the formula, the Pike formula, where the Milnor number is a linear combination of several Milnor numbers. This reminds me to Mihai Bihar's Tibar's general bouquet theorem. Also there you have deformations as critical points on the strata, and on each strata you have numbers, and it's also a linear relation. And it should be good to find out if they are the same.
Okay, yeah. Yes, I must admit, I don't know. That's a good question. Yeah, I just don't know. What I will say is that these WIs that arise, they arise as a result of certain associated group actions, Lie group actions, and the way they arise, it's not so clear. I mean, we've been able to do it for small size matrices, but these formulas get progressively bigger the larger the matrix. So I mean, it could be that gives a way to connect up these groups that enter into this with these corresponding free divisors and the thing that you're talking about with Mihai. That would be really interesting if that turned out to be true.
Okay, thank you for the answer. Are there more questions? If not, then we thank the speaker again. And we keep the transmission open for a moment, since we have to decide when the exercise session is going to start. 5 minutes from now? Yeah. In 5 minutes, we will start the exercise session, and we say goodbye to Jim, and we close this session.
Good hearing from you, Dirk. Great hearing your voice. Bye-bye.